Good afternoon. On behalf of Engineers Australia, I'm delighted to welcome you all to today's webinar, Future-Proofing Electrical System Design. My name is Megan Purdy and I'll be your host for today. Firstly, in keeping with our custom, Engineers Australia acknowledges the traditional custodians of the country throughout Australia and recognises their continuing connection to land, waters and community. We pay our respects to them and their cultures and to elders past and present. Before we get started, I would like to acknowledge that today's webinar is being hosted with Engineers Australia's industry partner, ABB. ABB is a leading global technology company that energises the transformation of society and industry to achieve a more productive, sustainable future. By connecting software to its electrification, robotics, automation and motion portfolio, ABB pushes the boundaries of technology to drive performance to new levels. With a history of excellence stretching back more than 130 years, ABB's success is driven by about 110,000 talented employees in over 100 countries. We have a rich discussion today with two presentations and our audience Q&A, so I encourage you all to please send your questions through to our speakers via the chat box. I'd now like to welcome our first speaker, Milad Mustafavala, Senior Product Manager, ABB. Milad is a Senior Product Manager in ABB. He assists clients with achieving their energy efficiency targets within electrification. For 15 years, he has been consulting with clients across small, medium and large enterprises, including commercial, industrial and government sector, supporting them to incorporate Industry 4.0 capabilities, data connectivity and analytics interface into their electrification systems. He is a practicing registered senior electrical engineer with expertise in power and energy distribution in electrification. Please join me in welcoming Milad Mustafavala.
A very good afternoon to you all, ladies and gentlemen. It's always a personal privilege and a professional pleasure to be invited back by Engineers Australia to be able to present again. The topic that we have chosen to present for you all today is around strategies for enhancing electrical resilience and safety. Today we will be discussing in terms of how to design electrical distribution systems to be more adaptive, reliable, and secure. The topics that I have chosen for you today is first of all around the key challenges that we are all facing as a cohort of electrical engineers. And then I will be presenting a set of design principles that I believe could be quite useful to tackle these challenges that we are facing. And then I'll quickly talk about some of the emerging technologies, and I'll wrap up the presentation with real-world case studies as well. That we've been able to assist clients. And I am also quite excited about Megan's presentation. It would be extremely complementary to what we will be covering today in terms of resilience and cost factor associated to that. So let's start. The electrical distribution network does face quite a significant amount of challenge in today's world in terms of efficiency and resilience. As electrical engineers, we are constantly tasked to bring up or design a system that can incorporate more efficiency and can incorporate additional resilience. This then call out for adaptive design and implementing adaptive design principles. And the reason for that is to be able to improve the flexibility and system response. And whilst we are supposed to provide for that as a cohort of engineers, we are also tasked or required to enhance the reliability and security of the electrical distribution system that we are in charge of. And these securities can be threats, it can be failures, it can be safety related threats, or it could be equally threats which are coming from cyber attacks. And in providing all these solutions as engineers, obviously there is a cost versus reliability that occurs. And balancing that investment cost becomes extremely important. Obviously, creating additional reliability factor into the system does possess additional cost, and making an electrical distribution system more optimal requires extra cost that we need to kind of count for and present to end clients. And lastly, the other challenge that's the state of affairs right now in our industry is the closeness, or the move from the generation that comes closer to the loads, and this creates additional requirement for higher fault clearance and faster clearing times. There's quite a number of cases that clients contact me, and they require to clear faults of higher values these days, because the source of generation is closer to the load, and they are also wanting to have a faster clearing time to be able to safely design their electrical system. So let's talk about some of the design principles that is kind of in line with these challenges. So the biggest challenge that we have is the aging infrastructure. Most of the distribution systems are outdated in terms of infrastructure, and that creates a limitation in terms of efficiency that we are constantly tasked to meet, and it also limits reliability, which is also something that we are tasked to achieve. Secondly, there is an increasing demand and a decentralization that's occurring within our electrical system with the introduction of distributed energy resources. And just to add to that, the electric vehicle infrastructure, they both create a complexity in creating or managing this decentralized distribution network model compared to the past. Cybersecurity threats are heightened now. They do have higher risk in terms of cyber attacks, and they definitely require security measures to be put in place to be able to create mitigation techniques or tactics. And to me, cybersecurity is all around implementing mitigation techniques to be able to reduce that level of threat. In addition to all these challenges that we are facing, climate challenges are there. Obviously, global warming is increasing the temperature, so the temperature performance of the assets and electrical switchgear are constantly on the increase. I can recollect from my 16 years of experience that the temperature that is required right now from most of the clients are pushing 20 degrees in Celsius more than what it used to be in the past in terms of operation, and wanting to ensure that optimum operation is there. And harmonics and power quality is also another issue that's continuing on. Total harmonic distortions and the loads that clients are using, the loads that the communities are using are much more sensitive these days. So what are the principles in terms of creating an adaptive design to be able to answer or mitigate these challenges? In my opinion, I think I was able to group these into four. Real-time monitoring and control is one of the first one, because our electrical distribution system is requiring to have a dynamic kind of response in terms of operation rather than a fixed operation compared to the past. So having or creating an adaptive system that can dynamically be controlled and monitored is very important. So that would then ensures or requires to be able to implement real-time monitoring. That's the first one. Second one is load balancing and demand response. So in order to create a stable and efficient operation, we need to encounter and incorporate a design that can, balance and manage that demand that changes all the time. Integration with distributed energy resources, with the renewables, with the solar and wind is extremely crucial, and it's a must these days. And scalability in the system architecture is also another important aspect that should be considered as a principle of creating an adaptive design. If you ask me in terms of how to design for adaptability, I can kind of summarize into three factors. Modularity is always the key or first element. So creating a modular architecture that can, react and increase at any time will make it future ready and future, proof. Having embedded sensors that can enable that flexibility is equally important. So these two go hand in hand in terms of modularity. Using predictive analytics and machine learning is also another brand new kind of technology that can assist us for designing for adaptability and creating or using those predictive analytics for fault detection. And interoperability becomes crucial too. Peer-to-peer communication. An example that I can provide to you is, for example, communication on 61850 that enables, multi-vendor communication regardless of the system in which the switchgear or electrical system is implemented. So let's now talk about reliability and security. How can we enhance reliability? Network redundancy is very important. So implementing a redundancy can increase that system resilience, and it can reduce the outage impacts if it occurs. Automated fault detection is another important factor. Being able to automatically detect and isolate faults quickly to minimize downtime and improving the reliability as well. And there is also reliability metrics that's quite important. Most of the clients do come to us and want to, improve reliability, but the way they have quantified that reliability factor is sometimes incorrect, and it calls out for, consideration and recalculation. And last one is what I call as electrical system hardening techniques, which means techniques that can strengthen the electrical system against any kind of intrusion or damages. So thermal monitoring, continuous thermal monitoring, having a network analyzing impact in terms of changing voltages, sags, swells, autonomous constant data logging activity to be able to see what's going on and understand what's going on, embedded arc flash protection. So these are the hardening techniques that can enhance the reliability of the electrical system. Now, in terms of security, there are threats to the electrical system. There is malware, ransomware, and kind of sabotage that can take place to any electrical system, and these are heightened and they are on the increase. Sometimes some of these security breaches are unwanted through subcontractors who unknowingly want to perform a job or perform, uh, you know, a test, and it happens in a very unwanted manner. Sometimes they are quite targeted. Sometimes they are quite, designed to infiltrate into a plant. And it's important to create security strategies that can segment and segregate part of the electrical system and require authentication in terms of any kind of access. And one of the ideas here is creating a design or an electrical system that can have compliance around, cybersecurity standard. One of the standard that I can suggest is IEC 61442-2, security level 2, which does ensure the operational integrity of the electrical system. Now, let's talk about cost versus reliability. Obviously, whenever we are wanting to improve or increase reliability, the cost increases. There's no doubt around that. There's no argument around that. And creating redundancy and failover in the system can definitely increase that cost. Now, what's important here is to be able to balance that security versus scalability factor and creating an effective design that can balance the two whilst optimizing the system performance. And optimization can occur through modular design. And if I'm to provide you with additional hint, I think creating a priority on the critical infrastructure as well in terms of cost effectiveness, I think that can also help and assist with the optimization. My colleague Megan will present further around these topics. Now let's talk about technologies and frameworks. So few of the emerging technologies that can assist us and you as the electrical engineering cohort can consider and utilize are obviously use of digital twins. So digital twins are enabling the detailed simulation of what's going on in real world on the switchgear onto a digital format, and they are able to provide that information through NFC, Bluetooth, mobile app or software as well. The other emerging technology is having the advanced metering infrastructure, so embedded metering and that data gathering that creates a granular data, picture for effective load management and fault detection. And it's very important to have high accuracy in those data that's being taken from your electrical distribution system. So let's summarize the design framework that can assist us in answering the challenges that we are facing today. So adaptability with modular design can leverage that flexibility and scalability. It can assist us. Creating reliability through redundancy can also create and ensure continuous performance and that fault tolerance kind of approach for us. And having security through segmentation, so segregating parts of the electrical distribution in terms of cybersecurity and creating, safety measures for service engineers and those who are operating the asset and the switchgear that can, keep the integrity of the system intact. And those are the three functions that is quite important. Now, Let's talk about some of the case studies that we've been able to assist few of the clients with these design criteria and approaches. First case is for an industrial client, and what we've been able to assist them with was around first power quality and measurement. So having a high resolution measurement assisted them to have a higher accuracy of detection inside their plant. We complied or utilized IEC 61557-12 compliance for measurement accuracy for this client that then enabled them to improve their uptime and obviously their reliability factor. Remote monitoring for this client and remote operation was also enabled real-time control and monitoring and enhanced their responsiveness and safety. And continuous thermal overload monitoring and continuous thermal monitoring of the switchgear together with arc flash protection increase their safety as well, and equipment longevity for this client. So overall, what has happened with this client was that we presented a reliability focused approach, and that improved their return of investment throughout an 18 months of period from 99.95 to 99.99. So if I'm to translate that, that would be 4 hours and a half of downtime to 52 minutes of downtime in that period. Next case is around a data center that we were able to implement a cybersecurity design for them. So a few of the factors that was important in this liaison was creating role-based access control for this client with secure firmware updates on the switchgear. And ensuring that that can assist them or control their segmented electrical distribution system. Embedding arc flash protection as well, created a faster clearing time for this client. Obviously, as you are aware, the data center landscape is constantly moving towards higher current and wanting to achieve higher fault currents up to values of 5,000 6,300 amp, and creating a faster clearing time for them is very, very crucial. So that's also another important factor that we've been able to propose in this project. And in addition to that, creating a continuous overload monitoring or continuous system monitoring also assisted them to achieve a higher uptime for this client. Next case is around implementing an adaptive design for a smart commercial building. So a couple of important factors that we've been able to provide in this project was around power quality and load profiling. So analyzing that power quality really helped with optimization, and that improved the efficiency and overall performance for this building owner. In addition to that, remote monitoring and predictive maintenance also enabled, reliability, additional reliability, and reduced the downtime for this facility. Embedded protection and thermal monitoring was also another key factor in this, adaptive design that created a kind of, advantage for this client because they removed any external devices or any needs for, commissioning, testing, and ongoing charges that they will incur for calibration of those protection systems that they have. Bringing that as an embedded functionality really help them to prevent any ongoing issues. And this particular client did have EV charging infrastructure as well, which also changes the load profile of their facility in a very dynamic fashion. So those continuous monitoring and constant thermal criteria and dynamic load profile assist them to balance their performance and their usage within the facility, and not only keeping their uptime high, but also making sure that the reliability does not drop and increases. And out of implementing these factors or creating these, criteria for this client, we've also been able to improve their energy cost as well, which is quite something to be proud of, I would say. So, just to wrap up and summarize what we have discussed today. Holistic system approach is very important. Please ensure that the systems that you are designing and incorporating in your professional liaison has future proofing. It does integrate adaptability, reliability, and security. And if you are considering these three, you will be guaranteed with sustained performance. Always make sure that you do a cross-disciplinary collaboration with other team members who are upstream, downstream. Just don't think that everything has to be within your own team. It's very important to kind of even propose and create this discussion and conversation with other teams who are involved within the project, and that can co-create a much positive final solution for the end client and people, stakeholders and people who are involved. And don't be afraid to innovate. Don't be afraid to utilize new standards that's coming in, and using the emerging technologies that have provisions for adherence to these new standards. These are all designed to assist clients to have a much more future-proof solution and creating a more efficient electrical system. So don't be afraid to do all of that. Also ensure that products and solutions that you are using and utilizing do call out for these pillars and factors. From ABB's perspective, we are very proud to be able to launch a new solution after 7 years of research and development that has consideration around these three pillars. And for those of you who might be interested to join us for this special product launch, please feel free to register, scan the QR code, and hopefully you will be able to learn more around these new solutions and technologies that we are very excited to be able to launch in Australia and New Zealand. With that, I would like to thank you for your time and attention.
Thank you, Milad, for your input. I'd now like to welcome our second speaker, Megan Mettiard. Megan is a Technical Director, Electrical at AECOM with over 20 years of experience demonstrating technical excellence, leadership and a commitment to advancing the electrical engineering profession. She has held a range of senior roles, including Electrical Team Lead for the Buildings and Places Group in Brisbane, and continues to contribute as a Senior Technical Specialist across major projects. Megan is a Design Manager, Project Manager, and Lead Electrical Engineer across large-scale, multidisciplinary projects. Her experience covers concept planning, full design documentation, project management, auditing and commissioning works. Please join me in welcoming Megan Mettiard.
Thank you very much for that introduction. My name is Megan Mettiard. I am an electrical engineer based in Brisbane. I've been working at AWST for 20 years now, and in that time I've worked on a large number of projects, predominantly in the defence and healthcare sectors. In my presentation today, I will be discussing two project examples which touch on the reliability and the adaptive functions of the sludging. So the first example project is to do with reliability considerations. When a project comes along that has reliability considerations as one of the key criteria, it's important to sort of sit down before you get started and really try and understand what the reliability that the client is after really means. So things like, do they have a defined reliability requirement? So a 4-line system or a 5-line system? Or is there just an overall concept of needing to have reliability? Is the reliability requirement for a particular system or for all systems? And what are the circumstances that reliability criteria needs to be met, particularly if it includes when an item is out of service for maintenance? What concurrent maintenance activities happen on the particular site for the project? And then resilience. Is there a different system that does the same thing, like a generator in addition to the mains power supply or UPS, versus redundancy being multiples of the same system, multiple generators, multiple UPSs? All of those questions make a really big difference in the electrical network design. So this particular project, I can't tell you what it is specifically, but I can say it wasn't a data center project, and it was a project that had multiple sites where certain reliability criteria was brief. So in this instance, the criteria stated was 10,000 hours reliability and a 99.99% availability. Now, what that really means, reliability, how long will the system perform its intended function without failure? A 10,000-hour system is about 1.13 years. 99.99% reliability. In this instance, that equates to a downtime of about 53 minutes per year. So that was the client criteria. The reliability modelling was undertaken. Took into account failure, repair, different failure rates, different availability equals for all the different subcomponents, and then that ended up being a system that looks like the system that was shown on the next slide. So you can see that there is some duplication of plant and some redundancy, but there are still some vulnerabilities, like one main switchboard, one UPS input switchboard, one UPS output switchboard, and one UPS distribution system. So despite meeting the client criteria, there are still some vulnerabilities within that system. There were maintenance activities factored into this network design. For example, there's a generator link box, which allows a temporary generator to be hooked up to let regular generator maintenance be undertaken. The UPS configuration was an N+1 arrangement, meaning that one unit could be taken out of service at a time. And there were dual distribution boards for critical equipment. So that system, as shown, met client criteria. So noting that the system on the previous slide didn't meet the reliability criteria that was set out, there were still considerations that needed to be talked through with the client, particularly around planned or unplanned outages and maintenance activities. So a planned outage is, as the name suggests, it's a plan. It's an outage that happens to carry out for maintenance of a component or an upgrade to a component. The systems that aren't required to be 24/7, planned outages can be arranged to occur out of those regular operating hours. But for systems that do operate 24/7, there's a whole series and sequence of planning and understanding of what alternative systems can be put into place to allow that maintenance to occur. There's some examples there on the screen of what that maintenance could be in a planned scenario. Maintenance of the transformers, taking oil cycles, regular generator maintenance around battery checks and just routine engine maintenance. In your switchgear, circuit breakers, basic RCBO testing, cleaning, etc. And then UPS units all have routine manufacturer maintenance requirements. So all those are known things that can be planned into your system. But then there's also the unplanned outages. So they're the outages that occur as a result of equipment failure or human intervention that causes a loss of supply. And unplanned outages can have really significant impacts on the system, and they can vary really significantly in the time to recover from that failure. So examples being a transformer failure, fault on switchboard, an incorrect switching procedure, or even accidental damage to cabling systems. So back to the project at hand. Knowing that the system, as shown there on the left, met the client criteria, there were then some discussions had in terms of those planning activities. Now, the project did specify withdrawal of switchgear to enable maintenance to be carried out while the system is still operational. However, failure of the main switchboard or any of the UPS distribution boards, or even a through-life replacement of those switchboards in a planned scenario would mean that these elements were out of service without an alternative supply. So in terms of a well-planned replacement, that could be, say, 2 days of downtime. But an unplanned outage due to fault could be weeks, or an unplanned failure of a switchboard could be in the order of months, not days or hours. So again, on this project, the UPS division that was in the network was 10 minutes of battery support. So it was really just designed to allow for that no break between the mains fail and the generators kicking in. It wasn't so much for long-term operation. Now, whilst comparatively rare, the risks do occur. So the discussion had to be had with the client around, is this an acceptable risk? So the answer that came back with this particular installation or project was that sometimes this is okay. So the next slide is going to show the configuration of the network that was actually provided in some instances, which went up to a 5-line site. Before I put that on the screen though, just wanted to, from a lessons learned perspective, stress that the conversations with the client to work out what they actually mean when they say reliability is vitally important. And stepping through each of those failure scenarios, maintenance scenarios, and what happens when a system fails, really key for them to understand what it actually means and to compare it to their operational procedures. It's also really important to understand, reliability criteria from things like the Uptime Institute or TIA data center standards is all about 24/7 operation. And then maintenance can't reduce the overall reliability of the systems. And that might not always be applicable to your client. So thinking through all of those scenarios and sitting down, the real key lessons in this particular project. So having had that conversation and having had the client decide, okay, some of our sites, the system that we've shown with the single points of failure, if you like, is acceptable. However, for some parts of the installation, it's not. And this is what it looks like. It's a full duplication of switchboards, generators, mobile generator link box, duplication of the UPS input-output switchboards, changing the UPS system from an N+1 to a 2N, and duplicating all of the mechanical systems as well. So, as you can see, it's quite a different installation compared to the 4 nines and 10,000 hours availability that was agreed for the month. So moving on to the second example project that I wanted to talk to today, it's moving away from defined reliability and into critical infrastructure modification. So this project is a health facility refurbishment and expansion. The site itself had infrastructure ranging from sort of early 1980s through to early 2010s. The project across the board involved modification to a number of main switchboards across the site, but this particular example that I'm going to speak to now is focused on one building, which was a newer building built in 2010 that had been designed knowing that it was going to be expanded in the future, and our project was the future. So when we first started, we had some initial key considerations that we needed to think about, things like the switchboard 61439 for the client, will they move to 3439 or an older standard? What does that mean in terms of being able to modify? Understanding that this was a hospital, and there were live critical areas of the site that needed to remain operational while we were to modification. So then there was staging and coordination that needed to be factored in, understanding the length of shutdowns that were appropriate on this particular site as well, very important. So moving into what was provisioned in the report basically. So there was an existing substation which was fitted with 2 that had space to expand to 5 300 kV transformers. There was a low voltage main switchboard room which had space in it for a future low voltage main switchboard. The existing low voltage main switchboard also had spare circuit breakers and spacers available for expansion. The generator hall had space allocated for future generators. Similarly, the risers had space for future expansion. There was some metering data available. There was some as constructed documents available. We also engaged some 3D scanning of the existing areas that we needed to interface with to assist in designing an expansion space. Now, that on face value all sounds really good, lots of provision for this future expansion. But when we got more into the nuts and bolts, there was some tricky realities associated. So the image there on the screen is the existing main switchboard. So existing main switchboard on the right, another generator switchboard on the left, but behind it, a lot of space there for future. Now, we had to add approximately 14 metres of new main switchboards into that space. The reality of constructing that in close proximity to the existing board through some challenges around how the electricians could safely do that work. You can also see in the image there is a lot of existing cables on a fairly hefty cable tray network, which is supported from a ceiling with some secondary steel structure. What isn't there is the actual tray for future. So we had to go down quite a bit of a rabbit hole with the structural team to understand what secondary steel that was there, what it could support, if we needed to add extra, how we could support it, because there was actually a void space between the ceiling that you can see there and the top of the room. That was also hard to access and a bit of an unknown as to what it was made of. So that provided some challenges as well. And then installing new circuit breakers on the existing main switchboard actually required full shutdowns of the switchboard. So these were some challenges that we faced in the main switchboard room. The next image is the main corridor that runs from the main switchboard room to the generator board. Now, again, lots of cable and cable tray, but also a lot of other services, and all encased in a burnt mesh. So when we had to add additional cable tray and cables for both reticulation to the generator hall, but also to access the risers, that was a challenge. And even just getting access to the slab to support the tray was a challenge as well. Inside the existing risers, there was physical spare capacity. You can see some empty tray there. However, it was blocked by the distribution boards and the outbound and submain handling that needed to stay live and was providing the sort of power and lighting to functional spaces within the hospital. The mechanical services subcircuit cable is also proposing to use these risers, and that was another thing that had to be added. So whilst the base build did have the provision for the future, utilising it was a challenge. And then this image is the generator board. Now, spare space for future generator. The wall was designed such that it would have the section removed with the attenuators and the air intakes in. However, there was a fuel line to the existing generator that was run across the top of the floor, right where the new generators needed to go. So that had to be chased in. But there was also a lack of clarity in the slab design for that particular hall that required a bit of chasing down by the structural team to make sure that it could A, chase it in, and then B, what weights we could add for the generators. So when I think back on the project, all of those challenges were overcome. The installation was a success, the client was happy, works the way it's supposed to. But if I put my hat on as if I was doing this again, what things would have made the expansion works easier in the original build were things like withdrawable switchgear in that existing main switchboard. If spare circuit breakers were actually fitted instead of spare spaces being provided. If there had been a separate future main switchboard room rather than space in the existing room, that would have alleviated a number of challenges with working in the live switchboards. If there had been separate riser space rather than having it occupied by the distribution system for the base build. A big one is access to comprehensive meter data. There was metering points throughout the site, but accessing that data and understanding the accuracy of it meant was quite a challenge. Having had on file protection studies and details, and even operating procedures around the generators would have made some of the expansion and interface works a lot easier to work through. And finally, if the spare capacity was provided in all facets of the electrical system, knowing that expansion would need to be installed, that would have helped. Now, I know you can't crystal ball every future scenario, but trying to put on your "how can I help future me" hat might provide some clarity in projects that come your way that might be designed for expansion. So I think about things like, is a digital twin going to be a requirement for a site? If I was starting a similar project from scratch, knowing it had to be designed for expansion, what are some of those emerging technologies? So yeah, digital twin, is that something that the client would be interested in? Talk to them about it. Having a proper discussion around what the expansion expectation is and what approach to that expansion would be acceptable. What operating scenarios do they foresee? And again, it's really hard to crystal ball, but having a conversation initially will make certain decisions easier. And I would also be having some serious discussions around energy monitoring systems and separating those from perhaps a traditional DMS. Each of those two project examples were multiple years in the design and construct cycles. So a 20-minute overview certainly doesn't do them justice. However, I do hope that some of these real world examples, provide some food for thought for when you are designing the next project. Thank you, Brad.
Thank you, Megan. Well, now it's our audience's turn to get involved. So please submit your questions to our speakers in the chat box, and don't forget to let me know who your question is directed to. A big thank you to everyone who registered or submitted questions while registering for today's webinar. So what I might do is kick off our Q&A with a question which came through from registration from Shin Shin in Victoria. Now, Malad, Shin's question is, what makes ABB cybersecurity different from others?
Fantastic. Thank you very much, Shin, for that question. And thanks a lot, Meg. As I presented during the session today, to me, cybersecurity is a mitigation technique. It involves processes or steps taken to eliminate threats. What would make our solution different is multi-factor authentication, layer of access protection to parameters, electrical parameters, having included anti-tampering features, having a role-based access within our architecture that distinguishes different people, different personnel, the owner of the asset versus the service engineer versus the viewer and the subcontractor would be my answer to that question. Meg?
Thanks, Malad. While I have you, I'll ask another question that came through registration. I can see that we've got a few live questions coming in right away, but the next one came through from Scott in New South Wales, and his question was, what is the IEC 61850 Goose communication capability of this generation SACE Emacs 3? Does the capability remain in the racked out state? Very specific questions there.
That's a very interesting and nice question. So thanks to Scott for that. Yes, 100%. We have always been able to do the 61850 Goose messaging peer-to-peer communication across our switchgear. Emacs 2 was also able to do this. Emacs 3 is also able to do this. So it does have that provision. And yes, it will provide that capability even in that state. I can also add that we will have a new eKeep Evo system in place as an architecture added on the new series that can enable this 61850 communication protocol for end clients.
Awesome, thank you. Megan, I might jump into a couple of those live questions which have come through. We've been waiting and they've all come through all in a rush. So Megan, we had a question. So big hello to H. O'Donnell who's watching live. How can the non-critical, nice to have elements of the design best be presented to the client that drives the most optimal outcome?
Yeah, look, thanks for that question. It's a really good one. In my opinion, and in a lot of what we do as designers, it's an open discussion. It's having the conversation with the client. Now, for me, I often go have a meeting, take drawings, step through the systems and the decisions and the reasons why. I mean, I'm a consultant, so often my job is to try and explain and walk perhaps a non-technical client through what the pros and cons are and what it means, and provide some recommendations. But it all comes back to communications.
Awesome, thank you. Well, I've got a question. Now, this question did come through from registration, and I might direct it to you both, if that's okay. And it came through from Lee in New South Wales. And the question was, what are the top 3 trends on electrical system design in Australia? So, Malad, who wants to kick off? I should maybe open it up?
Look, I can kick off. That's fine. Look, it's a really broad question, and in my opinion, it depends on what sector is, what the function of the particular system that you're speaking of. For me personally, some of the projects that I'm involved in are extremely focused on security and reliability of infrastructure, as well as more access to data and information like metering and metering at discrete levels as well, not just in one or two locations, and monitoring of circuit breaker statuses. But some other projects are sustainability focused. But like we saw in the presentation around reliability, there's a really big difference between, say, a 4 nines and a 5 nines system. So I'd stress again that discussion with your client around what does reliability mean to them. It's just so important to establish up front what they're really after.
Awesome, thank you, Emma.
Yes, and if I may just add to that, if I could, the brief that I mostly see these days and coming in more recent time are majorly focusing on safety, reliability, and that would be around continuity of service, so wanting to have minimum downtime, and efficiency, energy efficiency, that is, and that's the most that I see lately. Thanks.
Awesome, thank you. Megan, I'll jump back into one of our live questions, and this one came through from TL. Are cables ever run for expansion? This is commonplace for future expansion in shipbuilding.
Yeah, sure. Look, from my personal project experience, which is very buildings focused, not often. Things like bus duct and tee-off boxes have been run for future expansion, and it's a real balance between upfront cost and when the future expansion is envisaged, and a discussion around the practicalities of that. In an ideal world, great, it would be fantastic. It would solve a lot of problems for that expansion, but the realities are a little bit different when you start factoring in those issues.
Thank you. Another live question. So, Milad, I might ask this one of yourself, but Megan, please jump in if you would like to add. The question was, what challenges have you seen when integrating predictive maintenance tools into legacy systems, especially in industries like mining or utilities where equipment life cycles are long?
Fantastic. That's a very tactical and wise and experienced question. I'll start by talking about what I came across. Most of the time, the assets are that aged that even getting basic, information or having a very basic guarantee out of them is extremely difficult, especially within the utilities. I came across assets that was 55 years old, and because of the criticality that they have, replacement or planning for that continuous life cycle for that asset becomes extremely hard. And in those situations, it's mainly because, unfortunately, the utility client failed to have, techniques in place or plans in place to constantly check the life cycle or constantly, review the status, and they come across a point that the choice available to them becomes quite limited in terms of existing asset, and they need to plan for addition of new switchgear. In the mining approach, that's quite a different scenario, because with the mining end client, they do look into the asset lifecycle management in a much more thorough and detailed way. Obviously, if the mine site is impacted electrically, the operation is impacted, and that means the dollar and revenue value is equally impacted. Therefore, I have seen more significant investment when it comes to the mining application in terms of keeping that life cycle in place. Just to close off the conversation on that, the other thing that I do see is I feel that mining company do value the predict maintenance factor more than utility accounts, and I think that's I don't know whether we should call it a cultural shift or an engineering shift that we need to put as an effort to ensure that the utilities are also getting on board in that utilization of predictive maintenance factor and that life cycle management strategies. Thanks.
Thanks, Milad. Megan, we had a question that came through from Rommel, which I thought was a good question because it kind of tapped into something you spoke about, which was around communication with the client being very important. The question was, how do we persuade a client to allocate more lettable space, like rooms, rises for future services expansion?
Yeah, look, that's the $1 million question, right? And literally sometimes the $1 million question. Look, for my mind, it's a discussion up front around what the functionality of the particular installation is. Now, if it's a commercial lettable space, there may not be a future expansion requirement. It may not come into it. Versus if it was a highly critical data center that was known to be getting built in stages, where that future expansion space actually equates to dollars in that particular scenario. It's a bit of a horses for courses discussion, and I don't have the magic answer, I'm sorry, but it is a discussion that does need to be had in terms of what the end outcome and end goals and priorities for the client are.
Awesome. Thank you. Milad, I had a question that came through, just jumping back to one of the ones from registration. It was from Martin in Queensland, because he asked, what is RELT? So I thought I should address that for Martin.
Excellent. A very good afternoon to you, Martin, in Queensland as well. Reduce energy let through, and that is a function that we've been able to introduce in the past 3 years, if I'm not mistaken. And the necessity or the advantage that this item has is around creating a reduced energy setup for staff or service engineers who are working on the switchgear, specifically on our air circuit breakers and also on our molded case ranges. And the purpose of this module is to create a reduction in energy let through setting, as normally a setup for electrical distribution is set for to a higher rating in settings, to bring that down to a level that is safer for operators to perform any task or any commissioning or any activity that is there for them to perform. And we have had a huge amount of success with various different companies or end clients who are valuing or having an importance for safety for their staff and personnel and operator, and that's what the RELT module does for them. I hope that answered your question. Thanks.
Thanks, Milad. Now, the next question I was going to ask, because you both touched on digital twins, so I was really interested from both your points of view as where do you see digital twins becoming the norm? Megan, did you want to maybe kick off?
Yeah, absolutely. Look, to my mind, at the moment, critical sites, thinking sort of airports, key defence infrastructure, data centres. Now, having said that, I can also see that there are some sites that I would say meet that broad criteria, but would potentially push back on things like cost or the perception of it being another thing that needs to be learnt and managed. So I think there's an education piece around the benefits versus cost, around setting up, training, any licensing requirements with the client to determine what's important to them and having that sort of system become the norm. I do think with technology evolving and user interfaces becoming more interactive, it will make its way into our industries, as a norm eventually. But right now, I think some education around the benefits and costs are probably key to that becoming the norm.
Awesome, thank you. Milan, I'm assuming, did you want to add anything there? I should ask, sorry.
Yes, so most of the greenfield projects that I come across, specifically since 2022, whether they are government related or whether they are kind of privately held, they do require to add these newly technological approaches. But I have to admit that cost is definitely a factor that plays an important message there. Obviously, when we come across and provide that in terms of costing, there's not a big difference. There's no difference from our perspective, technically, as a vendor. People get on board and realize that quickly and try to grab the opportunity as soon as they can. Yeah.
Awesome. Thank you. Well, Milan, while I have you, Renault had posed a question, so big hello to you, Renault. How does someone plan to further optimize the T&D loss measurement when it has already reached a point where the accuracy class of metering infrastructure is at a saturation point? Goes on to say current metering infrastructure has 0.5 second class CTSs and 0.2 class audit meters over distribution transformers. If you could, and if I have messed that up, my apologies.
That was done well. Thanks a lot, Rorak. Sounds like you're looking at a perfectly designed system, and that's something that I struggle to come across in a month-to-month basis. That's a perfect system, and the accuracies are excellent, and they seem to be operating at a very excellent level. However, the only suggestion that I have there is taking a look at the feeder's perspective. Most of the time, that level of measurement that you're talking about there is either on the supply side or is either on the feeder side. And there is, a difference between the two because one is a greenfield and the other one is a brownfield. So that would be the only other comment that I can make to improve that further, to making sure that the whole system or electrical distribution system there does have that level of accuracy. And if you have it, then that's fantastic. You are on the money.
Megan, I've got a question that came through from Wilson, who's watching. Hi, Wilson. His question to you was, how did you navigate the non-compliances while working on the live main switch room on your second example? Were there any temporary dispensations required from ESB?
Look, thanks, Wilson. So there was a whole process that was stepped through in regards to how we approached that particular main switchboard work. It involved the builder, it involved the electrician, it involved us and the client stepping through what could and couldn't be done. In terms of what we actually did, there was use of forwarding. There was a lot of pre-running of cables and terminating in the room but away from the existing systems. And as far as some of the shutdowns that we were going to require on the existing main board, we ended up doing some redesign away from what we had initially planned to limit the shutdowns that were needed to only certain sections of the board as opposed to the board as a whole. So we didn't need any dispensations. ESB actually Electrical Safe Victoria. I'm in Queensland, so I'm not across that particularly, but it was all managed within the project team. But yeah, there were a lot of things that we had to work through to make it safe and to achieve the installation.
Awesome. Thank you. Milad, we had a question which came in from Una, and it was around what are the typical ROI for increasing efficiencies above 99.95% and also for adding duplication and redundancies to an electrical system?
Very good. Thanks a lot for that. We do have a return on investment models that we look into when it comes to change in those factors that you've mentioned. We do look into those ROI tools specifically because there is no two different clients who are having the same kind of approach, and they would like to kind of change and manipulate and see some of those changes and see what comes out of it. Sometimes we use those tools and try to improve it, and sometimes we try to kind of start and build a tool for that particular project. So we would be more than happy to talk further if you like, and if you want to get in touch with us, we do have a return on investment tool that we can develop and we can also consult with to get to what they are looking for. Thanks, Meg.
Awesome. Thank you. Megan, I've got a question from Margaret. Margaret also said, excellent presentations to you both, by the way. But her question was, Megan, have you done a reliability check for the simplest concurrently maintainable topology, and what reliability that system comes to? Oh my goodness, Margaret, that was a bit of a tongue twister for me.
Yeah, look. The short answer is not recently, and certainly nothing that I can remember the numbers off the top of my head. But I might actually pass to Milad because I'm sure that he's probably got some more information on the ABB side.
Thanks a lot, Megan. And great question, Margaret. Yes, we do have done models and reliability checks for specific clients. Just to be generic, within the data center segments, we have done that, and that has assisted the decision makers on those items. So more than happy to get in touch and have a conversation on that as well.
Well, look, I think we're actually coming up to the last question. So we've had an amazing Q&A. Thank you, everyone, for submitting your questions. But we've got James has submitted a question which I might pose to you both as the final question. And his question was, are there any tools and methodologies that you can recommend to help with future proofing generally? Sure. So Megan, do you want to maybe kick off?
Yeah, sure. Look, thanks, James. That's a really good question. And for my mind, again, it starts with that open discussion. Every project is going to be different. So there might be client guidelines that they already have rules around what type of spare they require in different elements of their system. And if they don't, it's a good opportunity to then sit down with the client and talk through, well, what does spare look like for you? What are the processes that you're doing? Whereabouts in your system is there value for money to provide spare capacity? And what does that look like? That's probably the best approach as a generic sort of an answer. I'm not sure, Milad, if you wanted to add.
Thanks, Megan. Yes, 100%. So thanks, James. In my humble opinion, as a personal kind of advice, there is always a hesitation on change, and there's always a reservedness from the traditional kind of approach. We are working in a segment or in an electrical industry that does have a lot of reservedness. So as a personal advice, don't be afraid to challenge new approaches, to challenge new functions, and don't be afraid to utilize those new functionalities, because those functionalities are developed out of consultation, conversation, and project examples that has ran for more than 5 years, 8 years, 10 years, even in some instance, and they are designed to improve the outcome. But when somebody is wanting to propose them or present them, there is an element of traditional approach that, oh, we have done this before, so why shouldn't we repeat it? Which is something that I don't see as a positive way, specifically when I put my engineering hat on, because we are there to create and we are there to, construct new approaches. So that would be my personal advice. As an ABB advice, I would suggest looking into the new standards and the new international standards that's being set and being rolled out. The changes, the amendments that they have is significantly improving the end quality, and always keep an eye out for new functions that's being released, and that will definitely help. I hope that answered your question, James. Thanks.
Awesome. Wonderful advice from you both. Well, that's all the time that we have for today. So please join me once again in thanking Milad Mostafabala and Megan Metiard for their time and input today. I'd also like to thank Engineers Australia's industry partner, ABB, for their support. Now, we would appreciate if you could take a moment to complete the short feedback form linked in the description box below. Your input really does help us to improve and plan our future sessions. So finally, thank you again for joining us today, and we look forward to seeing you at our next Industry Partners event. Good afternoon.